Today we'll be designing, building, and testing a brand new homemade rocket motor. By combining features from our highly successful Super Monkey motor and elements from Dan Pollino's giant K500 motor, we'll develop a brand new motor that is big, powerful, and pretty easy to build. This is the casing for a Dan Pollino K500 rocket motor. The motor we're going to be building today is our replacement for this motor. More about that in just a moment. Now, I've built two of these K500s. Here's a short clip from the first ground test. As you can see, that first one didn't end very well. We fixed the problem and we built a second one. That one worked great. This is the casing from that second test. So let me explain why we're building a replacement for Dan's K500 motor. When Dan was building and launching these motors back in the early 2000s, he was launching them in his Coyote rocket. The Coyote rocket, including this motor, had a total launch weight of 22 pounds or 10 kilograms. Now that's pretty heavy for a 3.5-inch diameter, 6-foot tall rocket. And that's why he needed such a large, powerful motor. We're going to be redesigning Dan's Coyote rocket with completely different lighter weight components, but we're still going to make it very similar in size. But since our rocket is going to be significantly lighter, we should be able to use a much smaller rocket motor to achieve similar launch performance. Dan's motor was rated as a K500, and that's a measurement of the thrust produced by the motor. Our motor is going to be shorter and less powerful, so it's not actually going to be a K500 rated motor. We're calling ours the K5R, which is just short for K500 replacement. We'll be building the new Coyote rocket in our next video, but first we need to design the motor. So we're going to take a look at every single component of the K500 and we'll decide what we want to keep and what we want to change. First is the motor casing. Now this is made from 2-inch Schedule 40 PVC pipe. We're going to stay with the 2-inch pipe, but ours is going to be much shorter. The K500 has approximately 29.5 inches of fuel in it. For our motor, we're going to have 14 inches of fuel. So why 14 inches? Well, no specific reason other than I decided that I wanted the finished motor to be around 18 inches long. And with the nozzle, 14 inches of fuel, and then the components that go in the bulkhead end, we should end up with a motor that's approximately 18 inches long. I've cut a piece of 2-inch PVC pipe 18 inches long. This is longer than what we need, but we can trim this down to size after we get the nozzle installed on one end. And that brings us to the nozzle. Now this is an area where Dan's building technique is much different than mine. To construct the nozzle for the K500, you start off with a 2-inch PVC slip coupling and a short piece of 2-inch PVC pipe. Several holes are drilled in the pipe and then it gets glued into the coupling. A divergent cone is made from paper and the nozzle washer sits on the paper cone. And then anchoring cement is poured into the PVC around the parts to form the nozzle. One of the main reasons Dan constructed his nozzle that way is because he needed a way to construct the nozzle as a standalone part and then attach that to the motor casing once it was completed. But there's a problem with that type of nozzle. Because the anchoring cement tapers down really thin as it approaches the end of the nozzle, it ends up actually getting destroyed by the exhaust coming out of the motor. Here's a close-up of a used K500 nozzle, and this gray part down here is what's left of the anchoring cement, but you can see most of the anchoring cement from that nozzle is just completely missing. To make our nozzles, we install any nozzle shaping components and the nozzle washer into a slip cap. The cap is then glued onto the motor casing, and the anchoring cement is poured down through the motor casing to form the nozzle inside the cap. This is the design we're going to use for this new motor. Now this type of nozzle does still have erosion when the motor is burning, but it's not nearly as bad as the erosion that takes place in the K500 nozzle. To form the nozzle, I've 3D printed this part. It has a small convergent angle on this side and a larger divergent angle on this side. The nozzle washer was placed onto the part while it was 3D printing, so the washer is trapped between the convergent and divergent sides. The nozzle washer is a steel fender washer with a 2-inch outside diameter. The inside hole needs to get bored out to be the proper nozzle hole size for this motor. So how do we determine the proper nozzle size for a new motor? Well, some of that is trial and error. For instance, if we build and test a new motor and it explodes, well, that's easy. We just have to increase the nozzle size until the motor doesn't explode anymore. But it's really helpful to have a starting point for that nozzle. So for that, we're going to use some data from 2 existing motors. First is our highly successful Super Monkey motor, and then the K500 motor. We're going to put the information about these motors into Richard Naka's SRM spreadsheet. That information will help us to determine a good starting point for the nozzle size of our new motor. I've put a link down in the description where you can download Richard's SRM spreadsheet if you want to try it for yourself. Here's the spreadsheet with all the information about our Super Monkey motor. Here it shows that we have a nozzle throat diameter of 8.786 millimeters, which is almost exactly the size that we use for that motor. In order to get the spreadsheet to give us that nozzle size, we had to set the maximum chamber pressure to 1100 psi. Now, I'm not saying that this motor gets to 1100 psi. I don't know if that number is accurate, and for the purposes of our project today, it really doesn't matter. We just need that number as a reference point. So let's set that number of 1100 psi aside and move on to the next motor. Now let's take a look at the SRM spreadsheet with all the data for the K500 motor. This one has a nozzle throat diameter of 23 millimeters, which is the actual nozzle size used in the K500 motor. To get that nozzle size, we needed to set the maximum chamber pressure to 1050 psi. Now again, I don't know if that 1050 psi is actually accurate for this motor, but it doesn't matter. What we have now is 2 psi reference points for 2 successful PVC motors, 1050 psi and 1100 psi. So if we enter in all the data in the SRM spreadsheet for our new rocket motor, what we should put in the chamber pressure is somewhere around 1050 or 1100 psi, and that will tell us a good starting point for the nozzle size. And that's what I've done here. This is the spreadsheet with all the details about our new motor. I've set the maximum chamber pressure to 1050 psi, and it shows that we should have a nozzle throat size of 15.846 millimeters. Now here in the United States, we use 64ths of an inch for nozzle sizes. So if we convert those millimeters into 64ths of an inch, we come up with 40 64ths. So this is a number 40 nozzle size. So before this washer was put onto the 3D printed part, the center hole was bored out to 40 64ths of an inch or 5/8 of an inch. Now we need to install this part into our 2-inch slip cap. So we'll need to bore a hole in the bottom of the cap. Let's head out to the workshop. For this, I'm using my lathe. I start out by drilling a large hole in the cap and then bore the hole larger until reaching the size needed to fit the nozzle form. Oh man, guys, I screwed something up on this build, but I discovered the problem early enough that we can fix it. So the reason I was using a washer with a 2-inch outside diameter is because it fits really nicely into the 2-inch PVC cap. But as soon as I put it in there, I realized there was a problem. This is going to be a very tight fit because we still need to attach the cap onto the PVC pipe. Now, if the washer is perfectly centered, it still fits inside the PVC pipe, but it's a tight fit. And we don't want a tight fit inside the pipe because we want some space between the washer and the pipe so that when we pour the anchoring cement down, it will go around the washer and fill up the nozzle. So the 2-inch washer is really not the right thing for this. So I found a washer with 1.5 inch outside diameter. I bored the center hole out to our number 40 size, and I 3D printed another one of the nozzle forms. So we're ready to install this into the cap. So there's the opening at the bottom of the cap. The nozzle form fits perfectly into that opening, And I'm going to use a little bit of construction adhesive to seal those two parts together. Now I'm not gluing the two parts together for strength. I just want to seal them together so that when we pour the anchoring cement in, it doesn't leak out the gap between those two parts. While I wait for that adhesive to dry, I can work on the PVC pipe. I'm going to drill 3 half-inch diameter holes near the bottom of the pipe. That's the section of the pipe that will get glued into the cap, so we won't see those holes after it's assembled. The reason for those holes is so that when we pour the anchoring cement down into the pipe and fill the nozzle, it will also fill those holes. And so the anchoring cement will be physically attached to the bottom of the PVC pipe. So in order for the nozzle to get pushed out or to blow out the bottom of the cap, it would have to rip through those holes as well as push the cap off at the same time. Now, is that completely necessary? I don't really know. We've seen other motors in the past that we've done that just had end caps on the end, and the end caps have been blown off. So this will just add a little extra strength to that, and hopefully we won't have a blowout. All right, the adhesive is dry on that nozzle assembly. It came out looking really nice. Now, one thing we need to do to this before we glue the pipe onto the cap, I've 3D printed this tiny little flat cap piece that goes onto the top of our nozzle form. And that's so that when we pour the anchoring cement into the nozzle, we don't fill the nozzle with cement. So I'll go ahead and get that snapped in place. Now we're ready to glue the cap onto the pipe. So I've got my PVC cement here. Now the brush that's in here is a little bit thicker than the gap between the washer and the cap. Now I could use it, but I would end up getting PVC cement all over the washer, and I really don't want to do that. So I'm going to use a couple of Q-tips that are a little narrower to get the PVC cement in the cap. Now we're ready to mix up the anchoring cement and pour the nozzle. Now I don't know how much anchoring cement I'm going to need because this is the first one of these motors I've made, so I'll just be sure to mix up some extra so we don't run out while we're pouring the nozzle. I've got a little flashlight here so I can look down and see when I've got the anchoring cement exactly to the top of that nozzle form. I let that anchoring cement harden for about 25 minutes. Now I'm going to push up through the nozzle with a rod to knock off that little plastic cap at the top of the nozzle form. Now I can cut the PVC pipe down to its finished length. Now we know the nozzle ends right at the end of the cap because the nozzle form was even with the top of the cap when we installed it. So if we measure up from the cap 14 inches, that's where the top of the fuel will be. But we want an extra 1.5 inches of pipe above the fuel because we're going to install some additional components up there. So I'll measure from the cap up 15.5 inches, and that's where we'll cut the pipe. Next, we're going to take a look at the ignition system for the K500 motor. Now normally for our small sugar motors, we would just use a small electric igniter that gets put up through the nozzle up to the top of the fuel. The igniter ignites the fuel at the top. The hot gases expand and head down the core of the fuel, igniting the entire core of the fuel cell. But that's a little bit of a problem with a motor this big. The K500 has a 1-inch diameter core hole and it's about 30 inches long. If we just ignite the fuel from the top and wait for that to make its way down to the nozzle end, it's going to take quite a bit of time. And that's a problem because in the amount of time it takes for that to get all the way down and light the entire core hole, a portion of the fuel at the top is going to be completely depleted before the bottom of the motor is even ignited. Also, the time that it takes to do that is a problem because that means that the motor is going to have a slow ramp up in power as that core is being ignited. We really don't want a slow ramp up in power when we're trying to lift a rocket off the launch rod. We need that core to be ignited fast so that the rocket gets a good powerful lift off. So to solve that problem, Dan used a powdered fuel ignition charge. A small piece of PVC was used to make a little cap with an electric igniter in it. The cap was then packed full with powdered sugar fuel and sealed closed. That igniter was placed at the top of the fuel. So when it was ignited, the powdered fuel would explode and blow a blast of flame down the core of the fuel, igniting the motor. That system works great, so we're going to use it on our motor. Instead of using a small piece of PVC pipe, I'm going to use a small piece of cardboard tubing. So let's get building our igniter. The piece of cardboard tubing is 3/4 of an inch long, and I've cut a little slot right here. I've got an electric igniter, and that wire slides into the slot, and I'll just lock that in place with a little dab of hot melt glue. I cut a small disc from a thin piece of cardboard, and I'm going to glue that onto the cardboard tube using the hot melt glue. And now I'll pack the fuel mixture into the cardboard tube. I left the fuel just a tiny bit down from the top of the cardboard tube, maybe just a millimeter. I'm going to mix up some 5-minute epoxy and seal the top of the fuel. We are almost ready to make the fuel for this motor, but we're going to need a few tools in order to do that. The core rod and the core rod alignment tool. Now this motor is going to have the same 1-inch diameter core hole as the K500, so we can use the same core rod and alignment tool that we used when we were making the K500. So first up is the core rod alignment tool. This is a 2-inch slip coupling with a 2-inch to 1-inch reducer and a short length of 1-inch PVC pipe. The inside of the 2-inch coupler was bored out so that it fits easily onto and off of the 2-inch PVC pipe. And then the coring rod. This is a solid piece of 1-inch aluminum rod. One end has been rounded so that it pushes through the fuel nice and easy, and the entire surface of the rod was polished with 1200 grit sandpaper for a super smooth finish. Now this coring rod is much longer than what we're going to need for this motor, but that's okay. We'll just be using one portion of it. There's one more thing we need to do to the motor before making the fuel, and that's cap off the top of the nozzle so that when we pour the fuel in, it doesn't fill the nozzle with fuel. So I've cut out a little disc of paper. We'll put some glue on that and drop it down into the motor. I've got that dropped in there. It's glue side down. I'm just going to tap it in place with a rod. We are just about ready to make the fuel for this motor, but before we do, there's two things we need to know. Number one, how much fuel do we need to make? Well, the fuel space in this motor is a little bit less than half that of the K500 motor. So I'm simply going to take the K500 fuel recipe and cut that in half. That will give us more than enough for this motor. And number two, we need to know how much fuel to pour into the motor. Now we want the finished fuel to be 14 inches long, but we can't pour in 14 inches of fuel because if we do, when we insert the coring rod, it will displace a bunch of fuel, causing the fuel height to rise by several inches. So I did some calculations based on the displacement of the casing and the displacement of the 1-inch coring rod, and I came up with, if we put in 11 inches of fuel, and then insert the coring rod, we should end up with a finished fuel height of 14.6 inches. Now that's a little bit higher than what we want, but that's okay because it's very easy to trim the fuel down after it's cooled. So that means we need to make a line in the motor casing 11 inches up from the top of the nozzle. Well, that's 4.5 inches down from the top, and there's no way for me to really easily get a pen or a pencil in there to draw that line. So I made a little tool to help with that. There's a little piece of a pencil glued on right here, and the distance between the tip of the pencil and the bottom of this wood is 4.5 inches. So if we just place that down inside the motor casing and rotate the casing, it will draw a line 4.5 inches down from the top, and that's where we need to stop when we're pouring the fuel. So now we're ready to make the fuel. Let's head out to the shop. I'll shake the powdered ingredients to mix them together for a few minutes. I'll get the coring rod ready by spraying it with oil. This will help keep the fuel from sticking to the rod. I'll turn up the temperature on the wok a little bit at a time as I continue to stir. Once the fuel reaches a soupy consistency, I'll keep a close eye on the fuel temperature with an infrared temperature gun. And then once the fuel reaches 220 degrees Fahrenheit, it's ready to be poured into the motor. This is much easier to do with 2 people. The core rod alignment tool is placed onto the motor, and the core rod is inserted until it pops through the piece of paper on top of the nozzle.
3 hours later.
All right, it's had a couple of hours to cool. Let's see if we can pull out the coring rod. Perfect. Absolutely perfect. Looking down the core hole, use a flashlight just to make sure that there's no pits or divots. It looks great. Now you can see here we just have a mess of fuel along the entire side of the PVC pipe, so we'll need to get rid of that. And then we need the top of the fuel to be 1.5 inches down from the top of the PVC pipe. That will give us our 14 inches of fuel. So I'll just scrape away what we don't need. Here's what the top of the finished fuel looks like. Between the fuel left over in the wok and the fuel removed from the top of the motor, we had about 200 grams extra, so next time I'll make a little bit less fuel. Now that the fuel is finished and we have a nice flat surface on the top of the fuel, we can install the igniter. The fuel is soft and pliable, so this just gets pushed gently down into the top of the fuel. The next component of the K500 motor is something Dan called the smoke element. It's something in the motor that burns really slow and produces a lot of smoke. It allows you to visually track the rocket high into the sky long after the fuel has been depleted. The smoke element is a mixture of 65% powdered potassium nitrate and 35% epoxy. Now I like the idea of a smoke element in the motor because these high-flying rockets can be pretty hard to see at those altitudes. So we're going to integrate the smoke element into our motor. We're just going to make it a little bit smaller. I'll start by grinding some potassium nitrate into a very fine powder. Then measure 86 grams of this powdered potassium nitrate. Dan used West System epoxy for his smoke element. That brand of epoxy is a little bit expensive, so I'll be using a similar product by Total Boat. This is a 2-part epoxy comprised of resin and hardener. It's a 5-to-1 mixture ratio, 5 parts resin to 1 part hardener. The containers have calibrated pumps that automatically dispense the proper ratio amounts. Because I've already made these smoke elements before for the K500 motor, I know that if I use 2 pumps of resin and 2 pumps of hardener, it will give me approximately 46 grams of epoxy. That's the amount that I need to mix with the 86 grams of potassium nitrate. The mixture is thick, but it's still pourable. This gets poured into the top of the motor, around the igniter, and all the way to the top of the motor casing. While I wait for that epoxy to harden, let me show you the last 2 PVC parts we're going to need to finish this motor. First, I've got a 2-inch slip cap. 2 small holes have been drilled in the top of the cap. And then I have a 2-inch slip coupling. The inside of this coupling has been bored out, so it now slides onto the 2-inch pipe like a sleeve. These get glued onto the motor using PVC cement. I'll put the coupling onto the motor and slide it down a bit. Then apply PVC cement to the cap and the top of the motor. The igniter wire goes through one of the holes in the cap, and the cap is glued onto the pipe. I'll then put a coating of PVC cement onto a few inches of the pipe just below the cap and slide the coupling up against the bottom of the cap. Now you might be wondering why there's a slip coupling installed there when it's clearly not being used as a coupling and actually doesn't even appear to serve any purpose at all. Remember, the smoke element is located in this portion of the motor and it burns very hot for a very long time. If we look at this used K500 casing, most of it is perfectly fine except up at the top where the smoke element was burning. There's a lot of deforming of the pipe and of this coupling. There's even a split on one side of the coupling. So the coupling is there to provide a second layer of PVC and prevent the smoke element from burning through the side of the motor. There's only one more thing we need to do to finish this motor. There's a small air space under the PVC cap. We need to fill that with anchoring cement. I'll mix up a small batch of anchoring cement. I'm going to use a plastic syringe to inject the anchoring cement into the cap. I'll keep adding anchoring cement until it comes out the hole around the wire. And then clean off the excess. This needs to sit for at least 30 minutes for the anchoring cement to set up. And the first Rotary Rocketry K5R rocket motor is finished. How does it compare to the K500? Well, at 18 inches, it's certainly a lot shorter. And our motor comes in at 1,955 grams. Let's go test it. No!
Give me the shirt!
No!
Give me the shirt!
No!
Hey guys, you don't need to fight over a Rotary Rocketry t-shirt.
We don't?
Show him where he can get his own.
Oh, cool! Wow!
Nice shirt.
Warning. Purchasing a Rotary Rocketry t-shirt may result in envy or jealousy from friends and family. T-shirt does not magically appear on your body. You need to purchase it and put it on yourself.
That was spectacular. Here it is in slow motion. That powdered ignition system does a fantastic job at lighting this motor. And then we had a full power burn for an entire 2 seconds. After the fuel was depleted, the smoke element burned for a full 1 minute. I could not be any happier with this motor. That was absolutely perfect. Now I do want to show you a side-by-side comparison of the nozzles on these motors after the burn. On the left here is the K500 nozzle, and you can see that there is a lot of the anchoring cement just completely missing. The divergent has been basically destroyed. On the right is our new K5R nozzle. It has hardly any deterioration. It's completely intact. So building the nozzle in the end cap like this is a great design. It's easy to build, works great, and has hardly any deterioration. Now, just like on the K500 motor, we have some deforming of the PVC pipe and the coupling up at this end from the heat of the smoke element, but the motor held together perfectly. That means we can move on to the next step in this project. But before I tell you the details about that, make sure you hit that like button. We really appreciate it. And be sure to check out the links in the description to Rotary Rocketry merchandise, as well as the new Rotary Rocketry plushie, handmade right here in the USA. So, the next step of our project. We're going to completely redesign Dan's Coyote rocket. That's the rocket that he was launching with the K500 motor, and we're going to launch our new lightweight Coyote using our new K5R rocket motor. So be sure you're subscribed to the channel. Don't miss out on any of our future content. Thanks for watching. We'll see you next time.